Back in 1977, the National Aeronautics and Space Administration strapped two mechanical explorers, each roughly equivalent to a small automobile in dimensions, into a launch vehicle and dispatched them on what was initially planned as a quinquennial journey to investigate the distant worlds orbiting our star. These twin spacecraft, christened the Voyagers, were engineered with a specific trajectory to conduct reconnaissance flights past the gas giants Jupiter and Saturn, along with the ice giants Uranus and Neptune, as they departed our stellar neighborhood permanently. Throughout their odyssey, these robotic ambassadors would relay scientific measurements and photographic documentation back to their home world. In an act of cosmic optimism, mission planners equipped each probe with a gold-plated phonograph record, a compilation of Earth's scientific knowledge and cultural artifacts intended to represent our species to any extraterrestrial intelligence they might encounter. This golden disc served as humanity's introduction to the cosmos, a greeting that essentially conveyed our planetary identity, our aesthetic appreciation of our world, our populous nature, and the complex yet fascinating reality of terrestrial existence. Nearly 5 decades have elapsed since that momentous launch. Remarkably, both Voyager spacecraft maintain active communication links with Earth. These mechanical pioneers have traveled far beyond the gravitational influence of our system's planetary bodies. NASA's official records indicate that Voyager 1 achieved a historic milestone in 2012 when it breached the heliospheric boundary, establishing itself as the inaugural human-engineered artifact to enter the interstellar medium. Its twin, Voyager 2, accomplished this same feat 6 years later in 2018, though following an alternative flight path. The region beyond our solar system's edge defies the sterile emptiness scientists once theorized. This frontier zone reveals itself as a dynamic and chaotic environment, populated with subatomic particles, electromagnetic disturbances, and the residual debris from stellar explosions that occurred eons ago. Despite operating across incomprehensible distances where their radio transmissions arrive as whisper-faint signals requiring Earth's most sophisticated reception equipment, both spacecraft continue their operational duties. The scientific community, including veteran astrophysicist Bill Kurth, whose collaboration with Voyager telemetry spans back to 1974, persists in analyzing how our star's activity influences the architecture of the heliosphere, that invisible protective envelope encasing our cosmic home. What began as a half-decade survey has evolved into a 50-year expedition. Rather than simple planetary reconnaissance, these missions have become humanity's first venture into the cosmic unknown. Accomplished without contingency protocols, maintenance capabilities, or fuel replenishment opportunities. Their performance has been so exemplary that they merit ceremonial redesignation as Voyager 31-10 models. Yet recently, these stalwart explorers approached what appeared to be their operational terminus. All indicators suggested an approaching conclusion: propellant reserves depleting, technological systems becoming antiquated, electronic components deteriorating. The narrative seemed destined for closure when these venerable Earth representatives experienced an unexpected revival. While not achieving complete restoration, NASA's engineering team succeeded in reactivating the dormant propulsion systems within these distant machines. Consequently, they now provide even more extraordinary scientific intelligence than previously obtained. Prepare for an extensive journey through the remarkable odyssey of two delicate mechanical scouts as they navigated the infernal conditions surrounding gas giants, encountered enigmatic celestial phenomena, and persevered through the silent hostility of deep space. Prior to the Voyager expeditions, the outer planetary bodies existed merely as indistinct luminous points against the nocturnal sky, ghostly forms barely discernible through telescopic observation. Our knowledge of their existence resembled attempting to identify a vessel's configuration through dense maritime fog. These distant worlds presented intriguing and aesthetically striking targets, yet remained fundamentally incomprehensible. The historical significance of the Voyager program lies in its unprecedented achievement, delivering the first high-resolution examination of the ring systems encircling our solar system's 4 giant planets. These robotic investigators provided humanity's initial detailed photographic documentation of the ring structures around Saturn, Jupiter, Uranus, and Neptune, celestial mechanics about which our understanding had been severely limited. Consider Saturn, whose ring system first attracted Galileo's attention in 1610. Long regarded as possessing a singular ring configuration composed primarily of frozen water and mineral fragments spanning from microscopic to multi-meter dimensions. Jupiter's ring system presents a stark contrast, extremely attenuated and translucent structures that remained undetected until Voyager 1's reconnaissance in 1979. These rings comprise predominantly particulate matter generated by micrometeorite bombardment of nearby satellite bodies. Uranus presents another fascinating case study. While ground-based observations identified its ring system in 1977, the Voyager spacecraft captured the first photographic evidence during their 1986 encounter. The probe obtained extraordinary backlit imagery as solar radiation penetrated the ring structure, revealing the most minute dust particles and demonstrating the ring's composition of predominantly dark, frozen, and rocky materials ranging from tens of microns to several meters in diameter. Neptune, classified as an ice giant, possesses a ring system comprising 5 primary components. This distant world remained largely mysterious until Voyager 2's approach in 1989. Operating at approximately 4.8 billion kilometers distance, Voyager 2 captured inaugural images of 2 prominent ring structures while simultaneously identifying more subtle rings composed of microscopic debris containing substantial organic compounds, which impart a distinctive reddish coloration. These ring systems exhibit intricate architecture characterized by irregular particle distributions and void regions created by the gravitational influence of small shepherding satellites. Voyager's detection of electrical phenomena within Jupiter's atmosphere marked the first confirmed observation of lightning activity beyond Earth's boundaries. Initially, Voyager 1 registered distinctive electromagnetic emissions termed whistlers, brief, high-frequency radio bursts generated by electrical discharges within Jupiter's atmospheric layers. The spacecraft intercepted these radio signatures while monitoring the planet's night hemisphere under conditions prohibiting optical observation. Subsequently, camera systems captured visual confirmation, brilliant luminous flashes originating beneath Jupiter's dense cloud formations. These electrical manifestations, illuminating upper atmospheric regions through discharge impacts, constituted the first direct photographic evidence of meteorological electrical activity on an extraterrestrial world. Regarding intensity and occurrence frequency, Jovian lightning phenomena exceed terrestrial equivalents. The electrical field magnitude reaches levels tens of times greater than Earth's, with individual discharge events releasing energies measured in hundreds of millions of joules, sufficient to incinerate a large dinosaur should one materialize in orbit, comparable to our planet's most severe thunderstorm systems. Lightning strike frequency within Jupiter's atmosphere can surpass thousands of events hourly, particularly within active cyclonic regions. These observations revealed that electrical phenomena on gas giant planets serve crucial roles in energy distribution, producing ionized particles and chemical compounds within upper atmospheric zones, where ammonia, hydrogen, and methane molecules decompose under extreme temperatures and electrical forces. These same processes influence cloud formation patterns and potentially establish conditions conducive to life in such harsh environments. While Jupiter commands respect through its age and gravitational dominance as an interplanetary powerhouse, Neptune's Great Dark Spot meteorological system holds the record for atmospheric velocity. During Voyager 2's 1989 flyby, this spacecraft first photographed the massive atmospheric vortex and recorded wind velocities, reaching 1,500 miles per hour. By comparison, Earth's most violent hurricanes barely achieve 200 miles per hour, essentially mild weather disturbances. The fundamental difference lies in energy sources. Unlike Earth, where irregular solar heating drives atmospheric circulation, Neptune receives minimal solar radiation. Consequently, the primary force generating these extreme winds originates from the planet's internal thermal energy, heat radiating from its core regions. Furthermore, Neptune lacks solid surface features. As a gas giant, its atmosphere transitions seamlessly into deeper layers. Without mountainous terrain or other geographical barriers to impede or redirect airflow, winds can achieve these extraordinary velocities. The Voyager program also provided our first compelling evidence that two frozen satellites in the outer solar system, Europa orbiting Jupiter and Enceladus orbiting Saturn, potentially conceal genuine liquid water oceans beneath their crystallized surfaces. The spacecraft documented extensive ice coverage on these celestial bodies, representing the initial step toward comprehending their internal architecture. Fundamentally, this information established the groundwork for discovering subsurface oceans, massive liquid water reservoirs that can persist due to geothermal processes and tidal forces generated by their parent planet's gravitational fields. These revelations established the foundation for subsequent exploration programs, notably the Cassini mission. Cassini's investigations revealed active hydrothermal features on Enceladus, thermal geysers ejecting water containing dissolved minerals and potentially microscopic organisms into space. On Earth, comparable hydrothermal environments provide habitats for diverse biological communities, prompting speculation about whether life might also exist within these moons' subsurface ocean systems. Encouragingly, October 14, 2024, witnessed the launch of a new exploratory mission specifically designed to conduct comprehensive Europa studies, aimed at determining the habitability potential of its subsurface ocean and identifying ongoing processes within that environment. This initiative represents a pivotal advancement in extraterrestrial life research and expanding our understanding of biological viability throughout the solar system. Voyager 2 also achieved the distinction of being the first spacecraft to document extraordinary phenomena on Triton, Neptune's largest satellite. Notable among these discoveries are geysers propelling gas and ice vapor streams to altitudes of 5 miles. For perspective, Earth's most renowned geyser, Old Faithful in Yellowstone National Park, achieves maximum heights of merely 200 feet. These observations clearly indicate active geological processes operating on this frigid moon, which possesses an atmosphere composed primarily of nitrogen with trace methane content. Subsequent investigations using the Hubble Space Telescope and atmospheric modeling have revealed that Triton experiences seasonal sublimation of surface frozen materials, which sustains these geyser activities. While extremely tenuous, the atmosphere fluctuates according to the satellite's orbital distance from the Sun, generating dynamic meteorological phenomena at temperatures of -391 degrees Fahrenheit. The photographic transmissions Voyager relayed to Earth arrived gradually, but represented eagerly anticipated glimpses into previously unknown realms that were beginning to divulge their secrets. Currently, utilizing advanced telescopic technology and planned future missions, scientific investigation of this frozen and enigmatic satellite continues. During 1989, both Voyager 1 and Voyager 2 completed their final planetary encounters. Shortly thereafter, mission controllers captured the legendary Earth photograph, designated the pale blue dot. This image presents our home planet as a nearly imperceptible minute speck, enveloped by cosmic particulates and brilliant solar illumination. Against the infinite backdrop of space, Earth appears fragile and diminutive. Observe that tiny point, it contains everything. Human history, suffering, musical expression, warfare, companionship, infant joy, scientific genius, casual domestic conversations. And that pivotal moment when someone first gazed skyward and wondered about the possibility of extraterrestrial existence. One might expect this to conclude like cinematic productions, dramatic finale, soaring musical score, followed by closing credits. However, the Voyager mission's reality chose a different path. Rather than peaceful retirement somewhere near Saturn's orbital zone, both spacecraft initiated a new phase, solitary navigation through frigid interstellar space. Contemporary Voyager data continues supporting our investigation of solar wind boundaries, the complex architecture of magnetic fields and particle populations that define our cosmic environment. These missions provide an unprecedented opportunity to examine the unknown beyond familiar territories and contemplate our connection to this limitless expanse. Until recently, the Voyagers navigated this cosmic sea relatively unobstructed, but now they encounter new, significantly more challenging conditions. The primary hazard is radiation exposure, specifically galactic cosmic rays traveling at near-light velocities. These particle concentrations far exceed those within the Sun's magnetic protective zone that shields Earth. These energetic particles readily penetrate electronic circuits, destroying components and creating statistical casualties recorded only in NASA databases. However, the Voyagers possess an unexpected advantage. Their 1970s-era electronics demonstrate superior durability and resistance to such effects compared to contemporary miniaturized and sensitive technologies. Additionally, magnetic field and plasma density measurements have increased dramatically over the past 5 years, suggesting that the Voyagers are traversing space regions about which our knowledge was minimal. This phenomenon may correlate with solar activity affecting even the most remote areas of the heliosphere, our solar system's protective envelope. While scientific consensus acknowledges that the Voyagers departed solar wind boundaries and entered interstellar space long ago, researchers continue debating the precise transition boundary location. This boundary, the heliopause, was traditionally conceptualized as a narrow, well-defined demarcation where solar wind encounters interstellar medium. However, recent research publications challenge this model. New theoretical mechanisms explain the puzzling observation that magnetic field orientation remained unchanged when Voyager 1 and Voyager 2 crossed the presumed heliopause. Investigation reveals that rather than a thin boundary, a thick, complex transition zone exists where solar and interstellar magnetic fields interact and intermingle. This means Voyager 1 has not yet reached pristine interstellar conditions, but remains within this substantial boundary layer. Current estimates place the authentic interstellar medium at least 100 astronomical units farther distant. This region remains inadequately studied and mystery-laden. At this intersection of two domains, solar and interstellar, the Voyagers continue broadcasting their invaluable communications from space's depths. Preserving operational capabilities for spacecraft that have wandered near our solar system's periphery for nearly half a century presents formidable challenges. This becomes particularly difficult when equipment deteriorates and physical maintenance remains impossible. Such circumstances materialized in November 2023, when Voyager 1 abruptly ceased transmitting coherent data to Earth. While signals continued arriving, they appeared as if the spacecraft had experienced cognitive failure or adopted an incomprehensible communication protocol resembling distress calls. Investigation identified the malfunction source as a damaged memory circuit aboard the spacecraft. Voyager 1 maintained command reception capability from Earth, but stopped returning data transmissions. Essentially, its communicative capacity had been silenced. The engineering team confronted an enormous challenge: re-establishing communication without physical access to the hardware. This represented genuine major repair operations requiring months of effort. Diagnostic procedures required engineers to transmit various test signals to Voyager while meticulously analyzing responses to determine which system components remained functional. An additional complication involved distance factors. Electromagnetic radiation and radio communications require nearly 24 hours for one-way transit to the Voyagers. This means each command transmission and response cycle constitutes a lengthy and anxiety-inducing process demanding patience and precision. Nevertheless, team persistence and engineering creativity achieved success. By April 2024, Voyager 1 re-established communication links. Transmissions from the solar system's edge became coherent and interpretable once again. The genuine miracle involved a technical achievement accomplished recently at NASA's Jet Propulsion Laboratory. Consider this scenario: a spacecraft presumed partially inoperative for nearly 2 decades suddenly returns to life. Voyager 1's inactive backup propulsion systems reactivated successfully. This occurred across the tremendous distance of over 166 astronomical units. For reference, one astronomical unit approximates the Earth-Sun distance, equaling roughly 93 million miles. Therefore, Voyager 1 currently operates about 15.5 billion miles from Earth. This represents an astronomical distance. As an illustration, maintaining constant 60 miles per hour automotive travel without stops would require approximately 29,000 years to reach Voyager 1's current location. Obviously, such verification remains impractical. The thruster shutdown resulted from sediment accumulation within fuel distribution lines. This condition threatened mission failure and loss of attitude control for Voyager's massive, nearly 13-foot parabolic antenna assembly. This antenna serves as our exclusive sensory connection to distant Earth, maintained with microscopic precision. Without this component, communication links could terminate, severing contact with a spacecraft positioned at such remote distances. Engineers ventured to test an audacious hypothesis. The problem originated from a malfunctioning power switch preventing thruster operation. This situation resembles an old television's power button becoming stuck, except this television operates nearly 15.5 billion miles away. Remote repair would require impossibly long-range capabilities. Regardless, their calculations proved accurate. In March of this year, corrective commands were transmitted. Following nearly 24 hours of waiting, the thruster began warming up and returning to operational status. This represented a modest celebration of engineering ingenuity and cosmic determination. Currently, Voyager 1 has resumed active service and continues its perpetual journey through interstellar space's dark expanses. The Voyager spacecraft demonstrate conclusively that human creativity, determination, and scientific passion can generate authentic miracles, even when these miracles occur across billions of miles. Naturally, nobody can precisely predict how much longer the Voyagers will maintain Earth communication capabilities. Mission administrators approach this question with measured optimism, hoping operations will continue until the spacecraft reach their 50th anniversary in 2027. We should persist as well, since this represents a significant milestone for any space vehicle, and for humanity equally. Eventually, and this outcome is inevitable, the instruments aboard the Voyagers will begin malfunctioning. Technical systems will simply deteriorate, operating under extreme conditions beyond Earth's and the Sun's protective influence, in absolute vacuum, extreme cold, and constant cosmic radiation exposure. Moreover, the spacecraft possess finite energy reserves. The Voyagers derive power from radioisotope thermoelectric generators that progressively lose efficiency. Annual energy production decreases steadily, meaning eventually insufficient power will remain to operate even critical instrumentation. Their illumination gradually dims, energy departs, and soon their mechanical hearts will cease functioning. We will no longer receive their transmissions, view their photographs, or detect even emergency signals. When the Voyagers become permanently silent, they will transform into mute emissaries proceeding toward infinity. They will serve as reminders that even within space's cold wilderness, humanity maintains a presence. Perhaps someday, across thousands or millions of years, some entity will discover them carrying imprints of our history, aspirations, and hopes. Meanwhile, we observe the nocturnal sky and express our gratitude. Thank you for your discoveries, for knowledge yet to be gained, and for demonstrating that regardless of the universe's vastness and coldness, human spirit consistently finds pathways toward illumination. Therefore, appreciation extends to the engineers and administrators of this legendary mission. Your contributions have benefited all humanity. If this presentation resonated with you, please support my projects through Boosty or Patreon. Your recognition enables continued creation of vital, profound, and enduring content. May our aspiration for stellar proximity achieve unified purpose.